So my name is Morteza, and I'm currently an assistant professor at Hertford University, UK. So today I'm just going to present some of our research stuff on soft wearable sensors for biomedical applications. So there is no definition for soft materials in terms of there is no direct measure to determine the soft or hardness of the materials. And elastic modulus is a kind of indicator to determine softness and hardness of the material. So as you see here, so we have a wide range of materials from extremely soft materials such as brain tissues, fat, to extremely rigid materials such as diamond or carbide. So among all of these materials, usually flexible polymers, foams, gels, and soft biological materials are considered as soft materials. So now, what are the advantages of having soft wearable devices? So as you know, so the rigid wearable devices such as wearable watches, they have very well established technology. And to date, they can measure multiple parameters such as steps, your calories, heart rate, ECG, and so on. But the main problem with these systems is that they usually have very poor contact with the skin because they are made of hard plastics. And that poor contact leads to noise and inaccuracy in the measured data, especially when the human body is on movements. So that means the data provided by wearable watches may not be very reliable for clinical use. On the other hand, so we have soft wearable devices. And these devices are just developing technologies. So that means there are a lot of challenges and opportunities in this area. And because these devices are made of soft materials, so that means when they are applied to the skin surface, they have kind of minimal discomfort. And because of the intimate contact with the skin, so that means they can get and they can have more accurate and reliable data from human body. The problem with soft materials is that the majority of soft materials, they suffer from the lack of functionality. For example, most of the soft polymers, they have very low conductivities. And that means they can be really used for sensing applications. And that's why the current trend is to combine soft materials with micro or nanoscale materials in the form of functional composite materials. And examples of functional composite materials based devices are flexible displays, wearable sensors, flexible solar cells, stretchable batteries, soft magnetic robots, wearable drug delivery, and etc. So to build an entirely soft machine or soft wearable device, so we usually need all of these components all in soft format. We need sensors, we need actuators, we need energy storage, we need communication, and memory. So in our lab, our focus is basically on the development of soft sensors and actuators. And the objectives of our research group is to develop soft sensors and actuators from functional composite materials and to seek bioinspired structures for the performance improvement of soft sensors and actuators, and also to look different ways for the compact integration of these components. And for today, so in coming slides, I only discuss some of our research activities on sensors only. So the first example, so here we have developed a carbon nanotube coated porous elastomer composite pressure sensors. So in the case of bulk soft materials, the problem is that when the pressure sensors are under compression, So first of all, their compressibility is very limited. And secondly, so when we have compression, we get kind of side bucklings. So to overcome these limitations, here we came to an idea to use porous elastomer coated with carbon nanotube network. And as you see on the bottom, the top right figures, so we can compress these composite materials to up to 80% without any side bucklings. And from bottom right figure, so you see the electromechanical characterization of our pressure sensors. So not only we improve the compressibility and buckling issues, as you see in this figure, so we have dramatically improved the sensing performance of these pressure sensors. And that's because in the case of porous elastomers, so these porous microstructures will come together during the compression, and that can bring a lot of these carbon nanotubes in contact to each other, which can result in increase of the electrical current passing through the pressure sensor. And for application, then we developed pressure sensor arrays for flexible foot insole. And as you see in the top right figure, so we can really distinguish and map the pressure distribution of the insole. And as you see in bottom figure, so we can kind of map and distinguish different patterns such as walking and running. And these data might be very useful for gait analysis and also fall detection and so on. So in another example, so we have developed silver nanowire elastomer nanocomposite sensors. So as you see from the top left figures, so these sensors are very flexible and stretchable. And from the top right figure, you see that we have a nanocomposite layer of silver nanowire elastomer sandwiched between two layers of PDMS elastomer. So on the bottom left figure, so you see the electromechanical characterization of these nanocomposite films. So we have measured the electrical, changing the electrical resistance versus strain. And if we define this slope of this curve as sensitivity or gauge factor, so we could get around 2 to 5 gauge factor for this nanocomposite strain sensors. And as you see in the bottom right figure, so the sensors can detect strains up to 70% with highly reversible electromechanical response. And to understand this behavior of our sensors, we then developed a computational modeling tool. So you see on the top right, top left figures that we have randomly assigned silver nanowires within the elastomer matrix in 3D, and then we calculated the position of each nanowire in 3D. And after stretching, we just recalculated the repositioning and reorientation of all of these nanowires. And then we looked at their connection, the connection between each two adjacent nanowires. And based on that, then we constructed the percolation network. And based on that, so you see that we could observe a very good match between our experimental results and also in our simulation. And the main reason of this behavior was the disconnection of a lot of these nanowires because of the stretching. And to show the application, so we have developed a smart glove system, wearable smart glove. And you see on the top left figure that we have kind of integrated our sensors on fingers. And also we have developed a custom-made miniaturized electronic chip where we can acquire the data and do the calibrations and send the data to a mobile device wirelessly. And as you see on the right figure, so we can kind of control a virtual hand by taking the inputs from our smart glove system. and this might find applications in prosthetics or robotic manipulation. So one of the challenges we had with the nanocomposite strain sensors was their poor sensitivity. In fact, we were not really able to detect very tiny skin movements. And to overcome this limitation, we just studied bioinspired microcracks for high strain sensing applications. So spiders, they can detect very tiny vibration and forces through their legs because they have slit organs on their legs. So the slit organ is basically a microcrack, structure which is connected to nervous system. So when an external force is applied to the legs, due to this opening and closure of these microcracks, a significant signal is transferred to nervous system. In that way, spiders can detect very, very tiny vibrations. So inspired from this design, so our idea was, so if you look at the bottom figure or curve, so in the case of a crack-free conductive film, so we have just gradual increase of the electrical resistance by strain because of the geometrical changes. Now, if we induce microcracks in this conductive film, so as you see, we expect to have much sharper change of the electrical resistance by stretching because the electrons cannot move from one side to another side because of this opening of these microcracks. So to generate microcracks, then we work with EcoFlex, which is a very soft material. And then we did plasma exposure of this EcoFlex elastomer to induce stiff oxide layer on the top. This stiff layer is like in nanometer scale, so it's a very thin stiff layer. And then we just coated the stiff layer with graphite film. So now if we stretch the structure, so because the oxide layer is very stiff, so the cracks will propagate on this layer, and then it's transferred to graphite film. So as you see on the top right figure, so when we stretch this composite multi-layer composite structure, we have this generation of this microcracks. And the good thing about our approach is that we can kind of control the microcracked area by just using a mask to prevent the plasma exposure. So based on this mechanism, then we developed microcrack-based stretchable strain sensors. And as you see in this in the left figure, the signal shift for a crack film is much higher than the crack-free film. And that means that we can get much more sensitive strain sensors. And you see in the right figures that we can detect very large strains up to 50%, and at the same time, we can detect tiny strains, for example, 0.5%. And to demonstrate the application in healthcare, so for example, we placed a sensor in the closing in the chest area, and as you see here, so the sensor was able to distinguish normal respiration and deep breathing. And in another example, so we just put or mounted a sensor in the radial artery of the wrist, and you see here you can somehow detect the blood flow pressure in that area. And for more practical applications, so we just took our sensors, and you see here we can really monitor the health rate and the respiration rate and pattern by just having these wearable strain sensors during the running practice. We developed these sensors, but one of the main challenges was their adhesion on the skin. So even though our EcoFlex-based sensors, they were extremely soft like skin in terms of mechanical compliance, but compliance. So you see here we had to do the taping to just fix the sensors on the skin surface and prevent the sliding. So on the right figure, so you see this is the microscopic image of the skin surface. And you see here the skin has a kind of multi-scale roughness ranging from micron scale to nanoscale. So this multi-scale roughness together with texture and soft topography of the skin, make a skin adhesion very, very challenging. So to tackle this problem, we just work with gecko-inspired microfibers. As you may know, so the geckos can climb and stick to different surfaces because of their like micro-scale hairy foot pads. So inspired from this, on the top right, you see we developed PDMS microfiber arrays. But surprisingly, we didn't get any adhesion on the skin surface because the skin has a kind of multi-scale roughness. So to overcome this limitation, so we just changed our method. So after fabricating the PDMS microfiber arrays, and we just transferred violin siloxane films to the microfiber tips, as you see in the skins on the left side. So this violin siloxane is a very biocompatible and a very fast curing polymer. In fact, we can solidify the viscous material in a few minutes. So what we did, we transferred this material to microfiber tips, and then we directly cured the viscous material on the skin surface. So as you see on the bottom middle figure, the SCM image, so as you see, because of this viscosity, so the material could penetrate into the different roughness levels of the skin replica. And you see in the bottom right figure, we could get quite strong adhesion on the skin surface because of this like tip adaptation to the multi-scale roughness of the skin surface. And then, so we did some characterization. So here on the left figure, you see that we could get adhesion strengths up to 18 kilopascal, which that time was one of the highest. So we run more experiments. So for example, on the top top right figure, so we kind of investigated the durability of our skin patches. So you see here, after around 300 bending and straightening cycles, still the patch is well attached to the skin surface. And also we looked at the long-term application because elastomers are known to irritate the skin after some long-term application. And you see here, we can see any kind of irritation after 24 hours of attachment. And that's because, so in the previous slide, you see there are a lot of air gaps and channels between these microfibers tips. And the air circulation between the skin surface and our patch is the reason why we didn't observe skin irritation in these patches. And then, so what we did, so we just integrated our microcrack-based sensors with our composite microfiber arrays. And you see on the top right figure, in the case of respiration monitoring, we have a very clear signal from our sensor. And even in the case of pulse rate monitoring, so you see here, compared to the previous slides, which I have shown, the signal here is much more clear. And we were able to kind of distinguish systolic and diastolic phases, and also detect P1 and P2 peaks. And all of these are like parameters to evaluate the heart performance. So therefore, in the case of soft wearable devices, their attachment to the skin is very critical and important for noise-free and accurate signal detection. So one of the main drawbacks of our composite microfiber adhesive was their poor repeatability. In fact, for every time of attachment, so we have to do that, transferring of polysilicon and film to microfiber tips. And in reality, so we were only able to use those patches only one time. So to improve that repeatability, so we just currently we are working on skin adhesive films. So we have kind of developed a super stretchable elastomer, which they are extremely adhesive to the skin surface, as it's evident in the top right figure. And to just explore the adhesion performance upon repeated attachment and detachment cycles, we just check the adhesion on a skin replica, and you see on the bottom right figure that we could get a quite like a stable adhesion over 30 cycles of attachment and detachment. They with around 25 kilopascal of adhesion strength, which is more than enough for wearable applications. And then we just integrated our skin adhesive films with stretchable sensors and electrodes. So as you see on the top right figure, so we can really detect muscle activities with high sensitivity through our stretchable strain sensors. And on the bottom figure, you see that we can develop very sticky, dry electrodes for ECG monitoring. And you see here, so we can get a high quality signal and just project that data in a mobile phone device. So another thing is, which is very important in the case of wearable sensors, is that the effect of environmental parameters on the sensing performance of these sensors. So to kind of investigate these effects, we developed a kind of custom-made environmental chamber with built-in linear stage. So with this setup, we can simultaneously control temperature, relative humidity, cyclic mechanical loading, and also the response from the sensor mounted on the linear moving stage. And to explore, so we have fabricated carbon nanotube-based strain sensors and kind of investigated the long-term impact of temperature and relative humidity on the sensing performance. So on the bottom figure, on the top figures, you see that the effect of temperature change on the sensing response of the nanocomposite is very significant. So on the top right figure, you see that the gauge factor of the sensor just decreased to 60% when the temperature was increased from room temperature to around 65. And in the bottom figures, you see that the relative humidity can really impact the sensor response dramatically. So that means in the case of wearable sensor technologies, so this is a very important consideration for practical applications, and therefore some novel packaging technologies or some new materials which are not sensitive to this unwanted crosstalk should be kind of developed. So in the case of future of soft wearable sensors, so advances in nanotechnology, material science, and microfabrication have led to the significant improvement in the sensing performance of wearable sensors. But so far, so the main focus was just to improve the sensing performance of different sensors by just using novel materials and formulations. But in my opinion, the reliable integration of all of these soft components is a grand nowadays. And so the future digital manufacturing process may overcome this limitation. And another problem with the current soft wearable sensors is that the performance of the soft batteries, memories, and communication units are still far behind silicon-based electronics. So that means we can really have an entirely soft wearable sensor device which can really detect the signals over a long period of time. In my opinion, the short and mid-term practical approach in this field is to hybridize the soft and hard electronics. So what does that mean? So we can develop soft sensors for the seamless integration in the skin and for a noise-free detection of vital signs. And on the other hand, so we can use chip scale components and hard electronics, conventional hard electronics for data collection, for calibration, and wireless transfer. But I believe that in long term, so multifunctional soft wearables will reach their full potential, and they should be able to monitor health condition and fitness status over a long period of time with minimal discomfort. So just to summarize my talk, so here I have just provided some examples of our research activities on wearable sensors, mainly physical sensors. And I have also shown that the adhesion of this kind of wearable sensors on the skin is very important and challenging for noise-free and accurate detection, signal detection. And also I have shown that the impact of environment can be significant on the long-term performance of wearable devices. So this is the thing that should be considered for practical applications. And so that's all from me, and thank you for your attention.
Okay, great. Thank you very much, Dr. Amjadi. I particularly enjoyed seeing how various examples from nature leads to intelligent design of systems. Just before we open the floor to questions, I forgot to mention during the introduction that the entire webinar today is being recorded, and it will be uploaded to a future YouTube channel and web page that SISMA is going to set up. So just to make you all aware of that. But yeah, we can open up to questions now. So if you have a question, in the bottom middle of the screen, there's a raise hand option. And if you push that, it can identify you as having a question to ask, and then we can unmute you. But just first of all, I have a question, which is you mentioned that in order to make an integrated wearable system, there's lots of different components that need to be made soft. So you have like the sensors and actuators that you work on, as well as energy storing and memory and so on. Which do you think is the hardest part of that to make a soft alternative to?
Yeah, so the problem with the integration is, so we have all of these multiple components, and we need to integrate all of these components in a tiny space to make sure that the entire subsystem is functioning. So the main point is how we can integrate, how we can make the interconnections, and how we can do, these wirings to make sure that all of these components are connected to each other. And in the case of, for example, soft batteries and memories, so it's still very, very challenging to really have a long-lasting battery or a powerful memory where we can, store all of those required data. So I think these are the main challenges that need to be addressed in the coming years. And I think, so one of the possible solutions could be used like digital manufacturing process, where we can have a CAD design of our entirely soft system. We can send it to a computer, and the digital manufacturing process can just fabricate that for us.
Okay, great. We have a couple questions in the chat as well. So first of all, Kia asks, can you please comment on the electrical properties of polyvinyl siloxane, if any?
So it has a very poor electrical conductivity. So it's basically as an insulating material.
Okay. And Rowan Armstrong asks, what are the main challenges posed by manufacturing of large quantities?
Yeah, so in terms of large quantities, I think, most of these examples I have provided, so they are basically like lab scale, examples. And sometimes it's very hard to get like multiple sensors with very repeated, signals, because they are just made by hand or by like very simple machines. So I think this challenge should be in large scale, is how we can fabricate multiple of these sensors and actuators, which they can have a similar kind of response to the external stimuli.
Okay, great. And also Zora has their hand up. So could you unmute your microphone, Zora, to ask a question?
Yep, thank you. Thank you, Dr. Amjadi, for your great lecture. I was just wondering, you said that you didn't see any skin irritation because of the air circulation that you have under your, the patch. So is that because of, first of all, is that because of those micropillars that you put under the adhesive layer? And also, when you add the sensing layer on top of it, do you still see the same, does it have the same biocompatibility with the skin? Or does it collapse or something like that? The micropillars. Thank you.
Okay, great question. So I think the main reason for having very low skin irritation in that case was because we had these micro pillars. So the micro pillars were just preventing the direct attachment of a planar, elastomer on the skin surface, which can prevent air circulation between the adhesive patch and the skin surface. So that was the reason, I think, why we got very low skin irritation. So in the case of regarding your second questions regarding the buckling, so the main reason was why we used PDMS microfillers was, they somehow have a like Young's modulus in the range of 1 to 2 megapascal. So that was very enough for us to just, apply our skin adhesive sensor on the skin surface. And in fact, the pressure which we were applying to our skin adhesive film was very low. So we don't really anticipate that that small pressure would induce any buckling or collapse of microfiber tips. And also we did some optimizations before application on the skin surface. So we played with aspect ratio of these pillars. We played with the density of these pillars to kind of identify and optimize, geometry where we don't really get this collapsing of these microfibers and pillars.
Okay. Well, thanks very much again, Dr. Amjadi. That was an excellent talk. And now we'll move on to, thank you, onto our second speaker, who is Professor John Rogers. He's the SQI Professor of Materials Science and Engineering, Biomedical Engineering, and Neurological Surgery at Northwestern Uni, just across the pond. He leads the Rogers Research Group, who specialize in soft materials, conformal electronics, nanophotonics, microfluidics, and microelectromechanical systems. He's garnered many fellowships and accolades over the course of his career, just this year being awarded with the Nancy Deloy and Roland V. Fitzroy Medal and the Herbert Pardes Clinical Research Excellency Award. And his talk today is Soft Electronic and Microfluidic Systems for the Human Body. So the floor is yours, Professor Rogers.
Okay, great. Hey, thanks for that introduction. It's a real pleasure to have a chance to take part in this webinar. Let me see if I can share my screen. I'm not seeing my PowerPoint application for some reason.
If you tried sharing the entire screen and then opening the PowerPoint and making it full screen.
Okay, let's try that. So can you?
Yeah, no, that's full screen now.
Okay, great. Well, again, it's a pleasure to be here and to share with you some of the things that we're doing in wearable electronics. I really enjoyed the previous talk, and it's fortunate because it really sets the stage nicely for some of the things that I'll talk about in my presentation, which really revolves around not only soft electronic systems for the skin, the human body more generally, but also some more recent work that we've been doing to integrate microfluidic functionality into those same platforms. So I'll start with a kind of a background, a little bit of a motivation, and a summary of the technical approaches that have worked pretty well for us in this area of technology, and then kind of give you a snapshot of what we view as kind of state of the art and in skin integrated, or sometimes referred to as epidermal electronics and biosensors, and things that we're doing in the context of scale deployments worldwide, development of these devices for addressing unmet clinical needs, and then kind of conclude again with some of our more recent work in extending these platforms to allow for capture and analysis of biofluids and biomarkers in biofluids. And so as a little bit of background, I mean, my expertise is in material science and engineering, but we're very interested in this interface between engineering and medicine. So we have very deep collaborations with physicians, clinicians across the medical complex here in Chicago, as will become apparent as I move through the various slides in my deck. So as was mentioned, in the previous talk, I think there's a lot of opportunities in thinking about electronics that are sort of reformulated away from their conventional, planar, rigid chip scale formats that you would see in consumer electronics gadgetry into designs that are more naturally compatible with the soft, curvilinear, time dynamic surfaces that you see in biology. And one point of integration that you could contemplate in that context would be between a man-made electronic system and the human brain. So ideally, man's most sophisticated form of electronics talking to and interfacing with biology's most sophisticated form of electronics. And that might be interesting as the basis for a class of tools that could be used to study fundamental questions in neuroscience research, but also as a platform for doing therapy and for treating various disorders of the brain. So we're very interested in brain interface systems, but also other vital organ systems of the body. The cardiac system is another one. It's electromechanical, so electronics in that context has obvious utility. I mean, the pacemaker would be a good example of a primitive style of electronics integrated with the heart that serves an essential function in cardiac patients. But like going way beyond that, thinking about fully integrated electronic systems that interface with the entire epicardial surface, just as a vision to think about. But we've also worked on kidney and bladder, spinal cord, peripheral nerves. But I'll focus on skin as kind of a next generation way of thinking about wearables, where that skin interface can in principle support measurements that really correlate quantitatively to kind of clinical grade assessments that are currently kind of restricted to a hospital or laboratory use. So that's the vision. I think the idea, again, the concept is to go beyond what's possible with standard wearables, as was mentioned by the previous speaker. So I won't belabor that point, but I think standard, kind of wrist-mounted devices are great for lots of things, but they can't do continuous ECG as a very basic, fundamental, measurement of cardiovascular health. You can get it episodically, but not continuously, and it's really a deficiency that flows back to the engineering designs, which involve bulky, rigid blocks of electronics loosely coupled to the body. And you want to kind of move beyond that to devices that look like skin, in terms of their physical properties, so that they can interface with the epidermis almost as a second skin, but fully instrumented with advanced electronics, biosensors, radio frequency communication capabilities, in some cases wireless power harvesting, functionality as well. And we've been working in this space for a very long time, almost 15 years. And at this point, we have a toolbox of all kinds of different sensors and radios and energy harvesting systems and on and on. I won't get into that, but all the details, to just give you a couple of examples. But the real vision is to bring ICU grade monitoring capabilities out of the ICU into the into the home and into forms that allow continuous rather than episodic measurements of health-related parameters. And data streams that physicians know how to interpret. So not step counts, but continuous ECG would be a good example of that, kind of vision. And so, as I mentioned, we've been slogging away in this space for a very long time. I think the good news is there are a number of strategies that seem to work pretty well, and we have our approaches, and a lot of other groups around the world are working in this space. I think it's very, very powerful direction for research with massive opportunities for broad societal benefit in terms of how we think about delivery and efficacy of healthcare, cost effectiveness as well into the future. So I think our first paper where we thought we kind of had a pretty good handle on how to do this was back in 2011 and got better in 2014. And I think the most compelling demonstration, at least for us, was just published last year. And I'll step you through this very quickly. I don't have a lot of time, but just give you an overview. And many of you may be familiar with these kinds of concepts. But this picture is showing that very first demonstration platform. It wasn't an integrated system with sort of direct clinical utility, but it was a platform that included, all the basic building blocks that you'd ultimately want for a skin interface electronic biosensor system. It's arrays of silicon CMOS electronic components, RF diodes. I think we had strain gauges, temperature sensors, antennas, all kinds of stuff, but built into an overall kind of heterogeneous hybrid platform, combining hard materials with soft materials, all with a goal to design a system that has physical properties precisely matched to the epidermis. So areal mass density, mechanical modulus, water permeation rates, really thermal mass, and so on, such that you could establish a long-lived interface with the epidermis with very minimal mechanical constraint or interface stresses that could drive delamination or otherwise create discomfort for the patient. And a lot of those strategies are exploiting geometry and microlithographically define elements of functional materials and then sort of embedding those into soft polymer-based elastomers, where mechanics design becomes almost as important as circuit design in terms of defining the layouts to get the kind of mechanics you want. This is an example of an interconnected filamentary serpentine mesh. It's kind of an electrode structure, but you can build devices directly into that kind of framework. When integrated with a silicone elastomer, for example, you can achieve effective Young's moduli that are matched to the skin, in spite of the fact that those filaments embed very high modulus brittle materials like silicon. And so that's from a mechanics standpoint, but for the geometry, it's also very powerful because it allows you to really conform to very heterogeneous, rough surfaces, as illustrated here in the case of a polymer replica of human skin. You can see how that kind of mesh type geometry allows for great contact over all except for the most challenging regions of topography. And that's good from the standpoint of interface adhesion, but also from the vantage of measurement fidelity, because it really reduces measurement impedances, whether you're doing thermal, electrical characterization, other forms of sensing where the skin is serving as a window to underlying physiological processes. And so with that kind of approach, it's materials, it's mechanics, it's electrical engineering, you put it all together, you can do a lot of different things, from the standpoint of sensing and measurement of health-related parameters, all the way from thermal, electrical, fluidic, I'll get into that in the second half of this talk, mechanical measurement, strain, motion, modulus, pressure. You heard some really interesting classes of pressure sensors, in this broader context in the previous presentation, but optical as well, even at the level of spectroscopic characterization of biomarkers, different things of that nature, and then time-dependent mechanics. So you can listen to body sounds, for example, as a almost like a wearable skin-like digital stethoscope. You can do all of that at this point. And so then the question would be, what's it good for ultimately? It's nice to build, various material systems and a toolbox of sensors, but ultimately you want to use those kinds of approaches to address real needs in clinical medicine. And we decided that this was probably the most compelling opportunity, at least from our perspective, and that is in vital signs monitoring of premature babies in neonatal intensive care units. And that kind of monitoring is essential to maintain proper health of the baby and to deliver proper care at the appropriate, because these patients are in very fragile health status, obviously, and you need to do full vital signs monitoring 24/7. And the way that that's currently accomplished is with relatively crude sensors, quite frankly, taped to the surface of the skin and then interconnected via hard wires to external boxes of data acquisition electronics. And that's really the way it's always been done. This is like 30, 40, 50-year-old technology, but that's what it is. It obviously has huge disadvantages for patients of this type, because it's a mechanical constraint. It's hard for the babies to move around in a natural way. It's difficult for parents to engage with their babies because of the presence of the wires. And then those adhesive tapes have to have strong enough adhesion to keep the sensors against the skin in the presence of interface forces that get imparted through the wires to the skin surface as the babies are moving around. And oftentimes that level of adhesion leads to tearing of the skin when the tapes are removed, and sensors have to be removed on a roughly 12 to 24-hour cycle so that the diapers can be changed and the babies can be cared for appropriately. And so I guess back in 2014, 2015 or so, we decided that, if the skin interface electronics can really work, then we should be able to get rid of that rat's nest of wires, get rid of the invasive tapes, and replace all of that without any sacrifices in data collection fidelity and accuracy with these wireless skin interface skin-like type of devices. And long story short, you can do all of that. And this is probably 4.5 year effort to get to this endpoint. It's just published last year. But you can replace all the wires, all the tapes with two devices, one that goes on the chest, and that's what's shown in this slide. That peanut-shaped structure, that's a filamentary serving antenna that's serving dual purposes. It's wirelessly harvesting power from a transmission antenna that mounts in the base of the isolate. And it's also doing real-time data communication, data streaming from sensors embedded into the platform. And in this case, the sensors consist of a pair of skin interface electrodes for measuring electrocardiograms, and that's what you're seeing plotted out here in the bottom frame. And it also has a clinical grade temperature for measuring surface temperature of the skin on the chest wall surface. In all the studies that we've done, the measurements are made simultaneously with clinical standard. That's the tape-on electrodes with the external data acquisition electronics, so we can evaluate the fidelity. You can see the lineup is quite good here. So from the ECG, you can determine obviously heart rate, also heart rate variability. From the amplitude of the R peak, that very sharp peak in these traces, you can determine the respiration rate. The temperature sends you a pretty good surrogate of core body temperature, because the environment of the isolate is very well controlled in terms of ambient temperature. You don't have to worry about variations in the ambient or airflows. And so there's a pretty good stable correlation to core body. But that's not all. If you want to do full vital signs and get rid of all the wires, and that's ultimately the goal here, you need another sensor that provides an optoelectronic rather than electronic interface to the body for measurements of blood oxygenation. And so this is another wireless battery-free skin interface platform. Instead of electric LEDs, in this case red and IR LEDs, lighting up out of phase in a pulsed operational mode, and then integrated in the same platform as a photodetector that's measuring backscattered light at those two wavelengths and transmitting continuously the readings to yield what is essentially a photoplasmography trace. And so you can get from this then SpO2. And with those two devices, you reproduce everything that's done clinically in even the most advanced neonatal intensive care units like those that we have here at Lurie Children's Hospital. So we've been on about 150 babies at this point, validating the technology. These are actual NICU patients. This is a picture of one. This is a 31-week-old baby, 1 week gestational age, that is. You can see the chest unit there on the chest, and then the wired electrodes that are simultaneously measuring ECG. Just to set the scale, you can see the hand on the right side of this view graph. That's a hand of Aaron Humphus, who's head of neonatology at Lurie Children's Hospital. And so we work very closely with him and his team, pediatricians, dermatologists, nurses, and parents, obviously, are volunteering their babies to participate in these studies. And so that worked pretty well. Like we published it last year. We've moved from the NICU into the PICU as well, so expanding the deployments into babies that are a little bit older, but still requiring continuous vital signs monitoring due to various complications and conditions associated with the babies. And so in this case as well, eliminating the wires has a lot of value. In this case is a picture of a mom interacting with her baby. You see the device on the chest. I talked about that one. The blood oximetry device is mounted on the foot. In this case, the wireless transmission and receive antenna is mounted in the base of the chair. And so it gives coverage over about a 1 meter radius volume, roughly, in terms of power delivery and data transfer. So you can see how this kind of works out, eliminates those cumbersome wires, and allows for very important types of engagements between parents and their child. That skin-to-skin contact has a very beneficial therapeutic effect on the development of the baby at this age. And so that's where we were last year. The Bill and Melinda Gates Foundation, the Save the Children Foundation, provided a large grant to take those technologies and to begin to deploy them into lower and middle income countries. And so we're in the middle of that exercise. We had to change the device designs a little bit, reduce their cost, increase their robustness to allow for use in these very challenging areas of the globe. But we've been able to do that. We're in Zambia, Kenya, and Ghana, about 1,000 devices for neonates, as well as for maternal fetal health as well. So straight through the intrapartum period, measuring mom's health of the fetus, and the health of the baby immediately after delivery. And the goal is 10,000 unit deployment through the end of this year. And I think we're on track for doing that. And so the latest devices that they're actually part of that deployment were published just a couple months ago in Nature Medicine. And so a lot of the same ideas, but different designs, expanded functionality, more sophisticated sensor suite, and so on. But the same kind of idea, wireless soft interface, skin interface senses for babies and mothers. So that's where we are. Not only the Gates Foundation, but we have deployments with Anthem, Janssen, as I mentioned, Save the Children. So I think we're in, 13, 14 countries at this point, and 5 continents or so. So this is on a good track. You might ask, is everything already done? And I would say definitely not. The opportunity here is now you have sort of a clinically validated scaled deployment of a platform into which you can drop all kinds of advanced sensors. I think that's the future. New materials, new sensor concepts can immediately be inserted into these devices to allow monitoring that goes beyond standard of care in the clinic today to enable deeper insights and more effective healthcare to be delivered to these very important classes of patients. So that's kind of the future as I see it. So lots of opportunity. That would be my message, opening up as a result of this work and other similar work going on at other groups around the world. So it's a very exciting area, I think, for materials science, biomedical technology, and so on. But what I've talked about so far is really just biophysical based modes of sensing, pressure, biopotential, temperature, sort of optical measurements, and so on. Ultimately, the body is a biochemical system, and in order to determine real insights into health status, you have to be able to measure biomarker concentrations in meaningful classes of biofluids. And so you can immediately think about blood, maybe interstitial fluid. Both of those classes of biofluids, though, require penetration of the skin. They're immediately classified as invasive technologies. The risks for infection, slow deployment, it gets very, very complicated very quickly as soon as you try to penetrate the surface of the skin. And so instead, we and others have been thinking about sweat as a pretty clean class of biofluid compared to saliva, for example, that can be captured non-invasively, unlike sweat and interstitial fluid. And thinking about sweat as a relatively underexplored but very important class of biofluid that has a lot of different biochemical content embedded in it that could be exploited to do these kinds of measurements of health status. And so incompatible class of lab-on-a-chip technology is essentially what it is. So full-blown microfluidics, but constructed out of materials, soft elastomers that are mechanically matched to the surface of the skin. And then we embed within those microfluidic platforms colorimetric chemical reagents that change in color by an amount directly proportional to the concentration of a biomarker of interest. And so we can really exploit the 20, 30 years of work that's gone on in the lab on a chip community, based primarily on rigid planar platforms, and really adapt those kinds of ideas for use directly as a skin interfaced wearable. where a dual-sided adhesive defines the bonding to the skin interface. Holes in that adhesive open up access for sweat glands to actively pump sweat into inlet ports in the back sides of these microfluidic systems. And the sweat glands then are the power source, essentially, for moving fluids around into these microfluidic channel networks and valving structures and analysis reservoirs and so on. And so in that sense, electronics becomes optional. So in many cases, you may want to add wireless electronics similar to the kinds of technologies I described for monitoring neonates, but for assessing, properties of the sweat. So you can do that, don't have to do that. And a lot of the examples I'll describe in the next 5 or 10 minutes do not involve electronics. The advantage there being that you can really reduce the cost of these sweat analytic systems to the point that they can be single use. And that's very powerful, because then you don't have to worry about cleaning the sweat out, refurbishing the devices, sterilizing them for a subsequent cycle of use. So we like non-electronic colorimetric readout schemes for that reason. Now, sweat has been looked at, in the past, and in fact, it serves as the gold standard for screening for cystic fibrosis. High chloride levels in the sweat is an indicator that a patient might suffer from cystic fibrosis, and so a lot of screening is done on pediatric patients using these kind of hockey puck type devices, rigid, sort of tightly strapped to the surface of the skin. These are macroduct devices, basically a coiled tube in a plastic housing. And so sweat released into that tube is collected. The tube is pulled out of that mounting fixture. The sweat is removed from the tube, inserted into lab-based chemical analysis platforms for chloride in this case, and then the assessment is made. The other way to do it is just use absorbent pad adhered to the skin with a tape. It's a very crude technology. Once the sweat has been collected, the absorbent pads are squeezed, and you harvest sweat in that way. But a number of different groups, have been looking at more sophisticated systems about parallel with our efforts. One at Berkeley, one at University of Cincinnati, one at Seoul National University in Korea. A lot of other groups as well, but these are some notable examples that use sort of electrochemical techniques and non-microfluidic approaches to assessing sweat chemistry, but without an ability to measure sweat loss or sweat rate, which turns out to be very important because the biomarker concentrations depend on sweat rate. And so you can't really make an accurate assessment of health status by just measuring the concentration. You also have to know the rate, because you got to calibrate the concentration depending on the rate. So great work by these other groups. So it's not microfluidics, it's not colorimetrics, it's a little bit different. So I think maybe complementary to what I'll talk about in the next 5-10 minutes. So our first paper was also in 2016, coincident with those other groups at Seoul National and Berkeley, but again, microfluidics. So this is kind of a first pass attempt. There we have 5 inlet ports in this case. One connects to that serpentine channel that's running around the perimeter of the device. In that case, we have a cobalt chloride doped hydrogel that undergoes a color change when exposed to water from purple, blue to red. And so just by visualizing the device, you can identify the fill front by the color change interface, geometry of the channel, the size of that inlet port. You can determine the total sweat loss, and if you know the timing, the sweat rate associated with that small region of the skin. And it turns out that local measurement of sweat rate and sweat loss correlates and calibrates to full body values. It's very important, but that can be proven out. If you know where the sweat patch is located, you can determine total body values. The other 4 inlets separately connect to these 4 circular reservoirs that embed these colorimetric chemical reagents, one changing color in response to lactate concentration, the other chloride, the other glucose, and the 4th pH. This is really multimodal chemical analysis system that also simultaneously does sweat rate and sweat loss, but very simple technology in a lot of ways. It's a molded piece of elastomer with some color changing chemistries embedded in. But as with the electronics, the mechanical property is super important, maybe even more important in this context, because here you have to establish a watertight interface to the skin in the context of a deformable curvilinear surface as defined by the skin on the body. So you really have to drive the modulus to very, very low levels to minimize those interface stresses so you can maintain this kind of watertight, robust adhesive seal to the surface of the skin. But you got to do all of that, and the paper goes into the details. This is a device mounted on the outer forearm of one of the grad students working on this project. And you can see robustness even in the context of the hair-bearing regions of the skin. But you can see that outer serpentine channel filled to, maybe 2/3 of its capacity, thereby determining sweat loss at this particular time point. And then with digital color analysis, you can extract out the concentrations of lactate, chloride, glucose, and you determine the pH as well. So I won't have time to go through the chemistries. I mean, there's a lot of material science in how you do these color changing measurements of different compositions, chemical components in sweat. This is chloride, uses a silver chloranilate chemistry. So you go from a light pink to a dark purple color, as chloride concentration changes across the range that's physiologically relevant for sweat. It's a very powerful way to do color sensing of chloride. There's some enzymatic assays that you can use for glucose, again, tailored to physiologically relevant ranges of concentration in glucose, about 100 times lower in concentration than blood, but you can do that. You can do other chemistries, lactate, for example, won't go through the details, pH as well. Very straightforward, you can do this. You can also embed valving structures, so you can do kind of a time sequential sampling of sweat chemistry. And so in this case, we have a whole collection, an array of reservoirs, each one of which is doing a different chemistry at a different time point. So we have capillary bursting valves that allow us to guide the filling of this platform in a sequential way. So reservoir 1 is filled before reservoir 2 and so on. And so you get some sort of equivalent time-dependent assessment of concentration. We're also doing sweat loss and sweat rate as well. And so there's a movie here. I don't know if you'll be able to see this, but I'll just play this movie. This is just filling. Doesn't seem to be working. Anyway, you kind of get the idea, hopefully, from my description. So you can compare the results obtained from a patch like this to conventional approaches for measuring sweat loss, absorbent pads, for example. Lines up pretty well. There's some variability. This is biology, so it's not precise, but you get a very good correlation, R-squared value about 0.85. You can also do colorimetric compared to HPLC evaluations of chloride concentration, something we're focusing on because of this CF screening application I mentioned to you before. But also it turns out to be very of very high interest to athletes and fitness buffs is electrolyte concentration in your sweat. And chloride is a pretty good surrogate for sodium. There's a little bit of potassium, but sodium and chloride is really dominant electrolyte species in sweat. And there you also get a very good correlation between colorimetric onboard sensing of chloride concentration, or these microfluidic skin interface patches, compared to secondary analysis of sweat extracted and then inserted into an HPLC system. So I think the low-hanging fruit here is in sports and athletics. And so we have a close collaboration with Gatorade. They sell a lot of sports beverage. Obviously, they're very interested in sweat loss and electrolyte loss because that's driving the sales of their core product. And so they've worked with us to take this sweat microfluidic patch out of the academic lab into the real world as a consumer product to pair with their sports beverages, to provide information to their customers around how much Gatorade they need to drink to replenish lost sweat, and what formulation of Gatorade in terms of electrolyte composition matches their own body chemistry. Everybody has a different electrolyte concentration in their sweat, and this device allows you to determine that precisely. And so we're deep into a joint development program with them. We've deployed on, 100 athletes, youth athletes at IMG Academy in Florida, but many others, probably 1,000 at this point, scaled. And this is the consumer form factor for this device. Is the GX sweat patch that we're developing with them. Has 2 inlet ports, one for chloride concentration, one for sweat loss, and both colorimetric, and that's the way it works. But in terms of engagement, this is a device that I was wearing on my inner forearm during a workout on elliptical, and you can kind of visualize, in real time how much sweat you're losing. And it's impossible to do that any other way because without a capture device like this, sweat is constantly evaporating from the surface of your skin. So it's a whole new way to sort of track exertion, right, in the context of an exercise routine or workout, something like that. It's pretty fun to play around with these devices. So they've, Gatorade has signed up a number of celebrity athletes. So this is Serena Williams, tennis player. If you follow tennis, there she is wearing our device. And again, it's informing people on how to best maintain optimal hydration level. That's the idea for performance athletes, or even just youth athletes, or fitness buffs, that type of thing. It's been launched in beta form, starting at the All-Star game, NBA game in February. This is Paul George. I don't know if people follow basketball. He's a pretty famous basketball player in the NBA, starting forward for the LA Clippers, and you can see it's on his arm as well. Anyway, I think we're mostly interested in medical applications, though, and so getting rid of that hockey puck macroduct device is something we're interested in. We were contacted by nurses who do this kind of screening at Lurie Children's Hospital, and we've been able to develop a device that eliminates the invasiveness of the strap and eliminates the need for the chloridimeter. So the analysis is done right on the device immediately after the sweat is captured, and that looks very promising. We've done extensive tests on pediatric patients. It's a very fun project, and we put fun graphics on the devices. It really enhances the engagement and gets the kids very, very compliant with the test, I would say. So anyway, it's all lining up. It looks quite good. So other kinds of applications as well. I think I'm out of time. Let me just go ahead and conclude with some of the things that we've been interested in wearables. It's all around skin interface devices, electronics, microfluidics. I think we feel pretty good about the progress we've been able to make, but a lot of other groups doing outstanding things as well. A lot of momentum, a lot of societal value in these kinds of projects, and tremendous amount of academic scientific content as well in nearly every field of traditional study, chemical engineering, mechanical, electrical engineering, material science, and so on. So everything we do is highly collaborative. I just conclude by acknowledging senior collaborators, both in engineering science as well as clinical medicine and sports. There's a number of folks there very important to our work. But ultimately, it's the students, the postdocs doing these projects. And I always like to conclude by acknowledging their efforts and generous support that we've received from sponsors over the years. So thanks again for including me in the webinar, and I'll be happy to answer any questions if there are any.
Okay, perfect. That was really interesting and exciting to see where things are going in the field. And it looks like we have a couple of questions already. We are running a little bit behind schedule, but we'll try to get a few questions in. So, Kaylee, would you like to ask the first question?
Hi, that was a really interesting talk. There's loads of really cool stuff in there. Thank you. I have a question about the neonate monitoring. So you mentioned that you had to reduce costs in order to distribute it in these kind of lower resource settings. So roughly, like how much did you have to reduce those costs by? How expensive is it now? Is it cheaper than what's currently done clinically?
Yeah, that's a great question. So I think, quite frankly, the Gates Foundation, the Save the Children Foundation wouldn't have funded this technology if they didn't think it could hit certain cost points. Otherwise, it's just not relevant for the countries that they're kind of most focused on and most interested in. And so the key metric is cost per patient day, because the devices are reusable. To kind of amortize the cost of the device itself over time, over some number of cycles of use. And the cost target was about a penny per patient per day. And so we think we can get into that range. There's cost projections in many cases, because the cost of the device is very dependent on the volume of manufacturing. It scales very strongly downward with volume. And so we had to do a lot of due diligence or respond to due diligence from the Gates Foundation around cost. And that's kind of what I can say at this time. A few pennies per patient per day. And that gets you in a range that's relevant even for Zambia, Kenya, Ghana, where we're deployed currently. The other part of your question is, how does the cost compare to what's done today? And what's done today in those parts of the world is nothing. There is no monitoring at all. And so that's kind of the tragedy of it all. And you might think about like what monitoring really means. And it means a lot, in terms of the ability to react quickly and provide care that's most valuable and delivered at the earliest time point. And that directly impacts the patient. But then there's another level of value to it, and that is in triaging limited medical resources, in particular limited numbers of healthcare workers. And so in some of these hospitals and clinics, and I spent 2 weeks in Zambia in December, you have tremendous numbers of babies and very tiny numbers of nurses. And the question is, how do you maximize utility of the nurses that you have on hand? And monitoring becomes critically important there, because you want the nurses to be focused on the patients who are in greatest need. And the outputs of these sensors provide quantitative information around, how you deploy those resources. So it's at those two levels. The cost in a level 4 NICU like you would encounter at Lurie Children's or Princess Women's Hospital here in Chicago is enormous. I mean, absolutely enormous. If you think about the monitoring hardware, the disposable electrode, everything is single use. And so it's not even close. I mean, from a cost standpoint, there's blowout advantage to these kinds of devices. But I think the value in those kinds of environments really is in enhancements in patient care. As I mentioned before, you eliminate risk of skin injury. You allow parents to interact with their babies and their child more frequently, and so on. So hopefully that answers your question. Maybe a little bit too much information there, but trying to touch upon all the key points.
No, that's great. Thank you.
Yeah, thank you. That was all really great to hear. So we take another quick question from Fredwick, if you want to unmute.
Yeah, thank you, Professor Rogers, for this fascinating presentation, actually. So my question is also in line with the practical utility standpoint. So can you kindly focus a feasible timestamp when these exciting technologies or the products can be into a real-time healthcare into the developing world to engage patients, not only with the diagnostics, but also with therapeutics?
Yeah, so the therapeutic, that's an interesting one. I mean, I think ultimately sensing is great, but if you could do sensing and delivery of some kind of therapeutic agent, that would be very powerful. And so we're certainly thinking along those lines. I mean, getting things through the skin barrier is not easy. If you want to think about drug delivery, I guess that's what you're contemplating. I don't know. We've thought about it. I think we're kind of focused on things that we can do now. In terms of a regulatory framework, once you're penetrating the skin, it's way more complicated. Even just getting devices onto human subjects for testing, you got to go through the IRB. And if you have penetrating microneedles or kind of thermal approaches to disrupt the stratifornium to do thermal drug delivery, it's just way more cumbersome to do that. And I want to do it. We see opportunities, near-term opportunities that we prefer to focus on at the moment. And so we did our first FDA submission earlier this month. The devices that we're deploying with Gates Foundation. We'll see how that plays out. My guess is we'll have approval for first set of indications within a month or two. We'll see. You never know. Look at that, soon. In terms of therapy, what we're looking at are haptic interfaces. So devices in one specific instance that are measuring swallowing and speech events in patients who suffer from aphasia and dysphagia, and the ability to provide some feedback to those patients not swallowing quickly enough, or they're not swallowing at the appropriate point in the cycle. You can provide that feedback just with a vibratory actuator built into the device. So it's kind of a primitive but still meaningful form of therapy that's going beyond just sensing. Kind of feedback to the patient can be very powerful in the context of rehabilitation for folks who are suffering from dysphagia or aphasia. But for therapy, we're looking at kinds of highly non-invasive approaches first, and then next stage would be around drug delivery. There's a lot of other groups kind of looking at similar things. So I think there's a lot of promising opportunities along those lines.
Yeah, thank you very much.
Okay, thank you again, Professor Rogers. I'll definitely be interested to go out and read some of these papers in more detail after today. We're going to take a short break now because we're running a little bit behind time. If anyone has any additional questions for either of the first two speakers, if you type them in the chat, then they can get back to you if they're happy to do that. But yeah, I suggest that we break now and aim to come back and start the next talk at 4:30 GMT. So once again, thank you so much to Dr. Amjadi and Professor Rogers for your talks. They were both very, very enjoyable. And I'll see you all back in about 5 minutes or so. Okay, welcome back, everyone. I hope you're feeling refreshed and ready for our final two talks of the day. And thank you once again to the two speakers that have already spoken. And thank you to Professor Rogers for answering Rowan's question in the chat. Our next speaker is Dr. Kia Nazarpur, who is a reader in biomechanical engineering at Newcastle University, where he leads the upper limb prosthesis control project. His research centers around the study of neuronal and behavioral processes to produce prosthetics with naturalistic sensory feedback signals. In 2018, Dr. Nazarpur received the UNESCO NetExplo Award for his project The Hand That Sees, a prosthetic hand which adjusts its grip based on feedback from an integrated camera. And his talk today is entitled The Ups and Downs of Machine Learning for Prosthetic Control. So I'll pass it over to you, Dr. Nazarpur.
Thank you very much, Greg, for the introduction, and I really enjoyed the previous presentations. What I'm trying to do is to share my screen, but it doesn't allow me.
Yeah, if there's a drop-out menu in the bottom right where you can share content. There's a button in the bottom right, share content, and then you can either share files to share the PowerPoint or share your screen and then make the PowerPoint.
That's what I'm trying to do, to share a screen, but it doesn't allow me.
Okay, what error message are you getting when you try to?
It's simply not functioning.
Okay. Is there any way you can email the slides to me and I can share them on my screen?
Alternatively, I can upload the presentation. I can just run it on the server.
Yeah, that would work.
Okay. %. Right. So while this is being converted to a presentable presentation, I just wanted to thank the organizers for inviting me. So I was going to talk about the ups and downs of machine learning, but then I saw the program, and it turned out that has a lot of sensing components in there. So I thought it might be a good idea to actually talk about the work that we do in Newcastle in terms of closed loop control of assistive technologies in general. I hope you would be able to see my my presentation now.
Yeah, I can confirm. We can see it now.
Excellent. So like I said, we are talking about the closed loop of control of assistive technologies, and I try to give some examples of where machine learning succeed, and then some areas that it has not proven successful. And then we're going to talk about some of the work that we do in terms of interfacing with the nervous system. For those of you who are not familiar with the prosthetic hands, the way that, generally speaking, a closed loop control of prosthesis hand is in the form of a movement intention takes place in the brain, and it travels down the spinal cord in a way that the muscles on the stump manifest that electrical activity. Sensors are placed on the skin, they pick up the electrical activity of muscles, and it goes to the next box, which is a decoding box, and we try to work out the different movement intention. A command then is then sent to the prosthesis, and then from the sensor feedback, we have sensory feedback going from the prosthesis back into the brain. So this has been the ideal scenario for control of the prosthesis for the past, let's say, 50 years. However, in the clinic today, still the muscle activity is recorded from only 2 channels. These 2 signals, for instance, one on the surface of the skin on the top side and one on the bottom side, they go to a unit which is called a feature extraction. Typically, it involves some bandpass filtering. And then these 2 bandpass filtered signal go to a very basic thresholding box. And in this thresholding box, if the 2 muscles are both quiet, non-active, nothing happens. The hand is in a rest mode. If one is active, the other one is quiet, the hand closes or the hand opens. And if both of these 2 muscles are active, wrist rotates or a grip is selected. And it's basically the hand is actuated. So this has been the state of art in prosthetics for the past many years, decades. This was an example of the prosthesis control, but it seems that Blackboard doesn't like these embedded videos. So in this video, what I would have shown you is that a person trying to move an object and to place into a tube for about 30 seconds, and they fail and they wouldn't be able to achieve this task. This was a video that was recorded by Alex Chadwell in Salford, and that shows how epically the current clinical procedures for restoring function are not good enough. So to overcome these challenges, the approach that I just explained is called the thresholding system. And in this thresholding system, we are looking at these 2 muscles. Over the past 10 years or so, there have been research in the area of machine learning by which we try to estimate the user intent with an intelligent way. In fact, many of the work that in machine learning has been done by folks at Northwestern in Chicago. And there are challenges in achieving this machine learning approach. A second way of controlling these devices is an approach that is called human learning. And in this human learning approach, what we are trying to do is to train the user to adapt to this new system, pretty much like when we buy a new bicycle and we learn how to use that bicycle. Then it becomes second nature for us. Now, in this presentation, I'm going to sort of give some examples of this machine learning and human learning approaches that are available. So from the machine learning approach, we know that the muscle activity, we can record muscle activity from many channels, like 16, 20 channels, all on the stump, and they look at the signature of different movements. Again, after a feature extraction, it goes to a neural network type or a general machine learning algorithm, and the actuation basically is commanded. So a decision is made. The machine would be able to learn what patterns these muscles are showing, and the prosthesis moves. I had an example here of another a video here that showed how a prosthesis can be controlled via this machine learning approach. That was a collaboration between Newcastle University and Edinburgh University. So in this video, we showed that people within within a response time of device response time of about 100 milliseconds, 120 milliseconds, they are able to grasp several objects and move them from place A to place B. And this is essentially the state of art in the control of prosthesis. I don't have the videos here, but I can show you what happens inside the device. So the EMG signal, the muscle activity, the electrical activity of muscles are recorded from 2 channels. And we have a real-time system that works out the patterns of muscle activity. For instance, the black signals showed in real time the decisions. But as you can see, there's a lot of incorrect decisions. So what we in that work, what we did was we had this post-processing system that looked at the likelihood of each decision, the correctness of each decision, and removed all of the mistakes from them. And therefore, we were able to achieve very good accuracy in terms of real-time control of a prosthesis. Now, like I said, these machine learning-based systems have been around for decades, and yet they haven't been able to translate into clinical practice. And there are several challenges associated with these new systems. I have tried to cluster these decisions into a triangle. On one side, we have the clinical challenges. The cost and time and money associated with deploying this advanced machine learning system is an issue. It requires significant staff training within the clinical sector, and obviously with that comes with very poor customer service. When things are out of calibration, it takes a huge amount of time to recalibrate devices. And of course, like many other clinical innovation, there's lack of evidence that these advanced devices actually improve the quality of life of users. From a user's point of view, we have several challenges. For instance, although we place these sensors on the surface of the skin, and in a stationary recording setup, our machine learning systems work robustly and reliably. As soon as the limb position changes or limb orientation changes, then these sensors are not calibrated anymore, simply because the muscle moves under the skin. So therefore, the propagation channel between the sensor or between the muscle and the sensor changes. And that is enough to push our machine learning algorithms into instability. Another aspect here is that when we train this machine learning algorithm within the laboratory, as soon as the users move outside the laboratory, they start adapting to these new systems. And therefore they show patterns of behavior that are not included in the training of those machine learning algorithms. Therefore, our machines do not adapt to the system, and then we have lack of after-use training data. Therefore, frequent recalibration are required, and all of these lead to poor or no generalization. Now, what we have tried to come up is to look at a new set of new principles to design these prostheses. These principles are a new controller should be as simple to learn as it can be. Like I said earlier, like riding a bicycle, the rules for that is very clear. And we would need to be able to provide continuous feedback of what user wants on the prosthesis. Therefore, they would be able to develop an inverse model of the system. So if I want to do X, I need to execute my muscles in that particular form. And ideally, it should be scalable at minimal extra costs. So all of these principles and requirements pushed us to the direction that we should keep our machine learning fixed, essentially zero machine learning, no learning whatsoever, and then put all of the load on the shoulders of the user to be able to learn for instance, controlling a cursor on the screen, on a computer screen, that maps directly to the control of that prosthesis. So here I had another video that showed how these prosthesis control mechanism can lead to very fast multifunctional devices. And we are working with a company called Covey based in Leeds to commercialize these techniques. So this was my third video, and it's a total shame that I cannot show this video. However, right after the presentation, I'm going to share the details of these 3 videos that are on our local repository, so that if you are interested in actually watching them, then you would be able to. But then we move to the concept of sensory feedback. So a lot of tasks that are around us is very difficult to achieve them without being able to sense the tip of our fingers. For instance, in this very example, picking at tiny grape is very difficult if you do not look at the hand and if you don't sense the tip, what the forces that you are applying at the tip of the finger. There is also speculation as to delivery of sensory feedback would help with the embodiment of the prosthesis, yet the research is still ongoing in that front. So essentially, in terms of restoring the sensory feedback, we would require to be able to sense what is happening at the tip of the finger, and then send these sensory signals into a set of biological and computational models, and that map whatever is sensed into the language that the brain would understand. And from that point, we need to be able to inject those signals into the nervous system, into the peripheral nervous system. So the challenges are multiple. So we have the sensory signals, basically sensing the world in terms of force, pressure, shear, and many other factors. We need to come up with biological models of the biological system, and the electronics to inject those electrical signals, and also the electrodes that are soft and compatible with the nervous tissue. So what I'm going to show you now is a couple of examples of the work that we have done in this area. So the first one is a development of this transversal multi-electrode flexible arrays. So we are talking about 110 gigapascal, and these are electrodes based on tungsten and titanium, developed for acute experiments. So on this shaft of the electrode, we have about 25 electrodes, and with the average dimensions of 50 to 75 microns. And these electrodes are implanted in the peripheral nerve. So here is an example that we have. We put the electrode on the sciatic nerve, and we try to aim different branches of the sciatic nerve within the main body, with the main trunk. And we are aiming to stimulate with these electrodes 2 different branches of the sciatic nerve. And if we are able to stimulate 2 different branches, then these 2 muscles on the periphery are stimulated selectively. Here are some results. For instance, at the threshold level of stimulation, then about 66% of our electrodes on the shaft are selective. And as we increase the level of the current, then these selectivity reduces, because you end up cranking up the current. Another aspect of the work that we've done is in fact by developing electronic hardware that enable us to actually deliver that stimulation via that sensor. So here is the work that we've done in collaboration with Imperial College, and we have an application-specific IC that in the scale of about 4 millimeters by 4 millimeters, and we can stimulate up to 32 different channels individually and concurrently, up to 3 channels at a time. And these would basically significantly increase the bandwidth by which we can communicate with the brain. Importantly, all of the system is implantable, and the communication unit would sit under the scruff of the animal, and then there's a wireless communication via a coil for power transfer and data transfer. So we've tested these systems in rodent experiments very recently, and we are on the way to, in the long term, translate them in human experiments. So simply to conclude, the work on prosthetics has this impossible triangle to balance. So user needs are one aspect, and that are currently, in the way that technology and academic work are developed, user needs are not taken into account, or users they are not involved in the development of the research from the outset. Another aspect is, of course, the clinical and regulatory consideration for these implantable technologies, and then the fluid nature of regulatory affairs, especially now when the country is coming out from the European Union. So all of these new regulatory considerations have to be taken into account. From the data point of view, currently when the users leave the clinics, clinicians have absolutely no idea of how often these prostheses are used and how well are these prostheses used. Alex Chadwell, again in Salford, have come up with a very nice system to quantify prosthesis use. For instance, around the clock, each ring is a 24 hours, and there are 7 rings representing 7 different days in a week. For instance, the orange color represents lack of use or inactivity, and then the bluish colors use the activity. So here is a midnight, and this is 6 o'clock in the morning. And you can see that it shows during the night people do not use their prosthesis, and during the day they are using. But then there are episodes of inactivity and during the day. So if we are be able to develop these better assistive technologies, we would need technologies for activity monitoring that support the hypothesis that these devices actually enhance the quality of life of people. And it also allows us to develop to new methods to study sensory motor neuroscience. What happens if you want to move a prosthesis, and is it a naturalistic feeling in that prosthesis? So this was the work of the team. Particularly Han Jung Woo, Agamemnon Krasoulis, who both of them actually studied their PhD in Edinburgh, Matthew Dyson, and also Carolina Silveira, who did a lot of work on the sensory feedback. So this is the end of my presentation, and I have to say that my team, we are moving to the University of Edinburgh, to the School of Informatics, and we're joining the Institute of Adaptive and Neural Computations, and there are several postdoctoral and PhD positions in my laboratory that are open from September, and I'm looking for people with skills in embedded electronics, Internet of Things, and machine learning in general. I do apologize for those videos and not being able to show them today to you. Thank you.
Okay, thank you very much, Dr. Nazarpour. Again, that was a very, very interesting talk. If anyone has any questions, they can now raise their hand or ask them in the chat. My own question regards the interfacing. So as far as I'm aware, you're interfacing with the muscles themselves, or with the skin, with the EMG sort of output from muscles. Is it possible to interface directly with the brain or with the nerves themselves? And if so, what are the advantages, disadvantages of such an approach?
So yes, we are from there are two routes here. One is from the brain to the muscles, and then to the prosthesis, and the other one is from the prosthesis to the brain. In the forward loop from the brain to the prosthesis, yes, we are picking up the electrical activity from the surface of the skin, the so-called surface electromyography signals. It is possible to also record from the muscles directly. It is possible to record from the nerves and the peripheral nerves, and it's also possible to record from the cortex. And in different stage of our research over the past 10 years, we've done different ways of measuring this movement intention. And obviously, the challenge or the trade-off is basically you gain and you lose something. You gain the resolution of access to motor, but then what you lose is the safety of surface electromyogram signals. So that's the trade-off. There are new research down in London by Dario Farina, and what they are trying to do is to record from many sensors on the surface of the skin, like hundreds of sensors on the surface of the skin, and trying to back project and estimate what is happening on the nerves. So they would be able to have access to the neural commands non-invasively from the surface of the skin, which is engineering-wise and from a signal processing aspect is really exciting. And the challenge is that deploying that in real time in a real prosthesis, and then the inaccuracies that they might appear because of limb movement.
Okay, thanks very much. Do we have any questions from anyone else? Oh, so Rowan asks in the chat, have you created your own EMG signal database, and are there any publicly available databases?
Yes. So the answer to both of questions is yes. So all of our data is online and is publicly available. And there is a very good database called NINA-PRO database, and is based in Switzerland. And our data is downloadable from that database as well. So it's a repository of for EMG signals, specifically for prosthesis control, and that different laboratories from around the world are uploading their data on that repository. So simply it's called NINA-PRO. So you would be able to go there, download, and I think at the moment there are 12 databases available there.
Great, thank you. That's really useful. Just finally, a very quick question from me. When you first fit a patient with one of these prostheses, how long roughly does it take them to learn to use it in a competent manner? And what are the sort of main factors affecting patient uptake of a prosthesis like this?
So answer the first question. In the clinic, it takes about 2 to 3 days for the first fitting, the socket fitting, getting a good fit, and then the user would be able to get a hang of the basic control. From the machine learning point of view, the evidence out there suggests that it takes a couple of weeks. In fact, the work from the Northwestern University groups suggests that it takes about a couple of weeks for the user to get a hang of a machine learning based system. The human learning based system is significantly slower because of the training nature of the work. So it could take up to a couple of months for the user to get a good hang of the controller. Motivation is a very key factor, and engagement is very key in the learning of a prosthesis use. The concept of serious gaming has been introduced in the context of prosthesis, although the literature does not support the transfer of a skill from a game to a prosthesis just yet. When you talk to prosthesis users, there are several factors that determine the long-term use of a device. Number one is the function of the device. Number two is the psychology around rehabilitation, nothing to do with the prosthesis, but whether the user or the patient is ready to receive a prosthesis or not. So these are the two factors. The look of the device, the static aspect of the device is also a factor.
Okay. Yeah, really fascinating stuff. So thank you once again. And also welcome to Edinburgh University when you do move up here soon.
Thank you very much.
So now we move on to our final speaker of the day, who is Roy Hotrabavanon. He's the CEO and co-founder of Player Data, which is an Edinburgh-based software and electronics company that specializes in wearable technology to monitor performance in sports. The company's received many rewards and acknowledgements since their founding 3 years ago. And Roy himself received the Made in Scotland Young Innovator of the Year Award in 2018. And he's a Royal Society of Edinburgh Enterprise Fellow. So welcome, Roy. And he's going to give us a talk now on a journey in tracking athlete performance.
Thank you very much. Thank you for the introduction. It's great to be here today, and I hope you can see my screen okay. Hopefully that's come up all right.
Yeah, now we can see it.
My talk today is a little bit different to the ones that you've heard earlier today, because my perspective has been, and I'll get into it in my talk, has been to take an idea and a concept, test it, develop it, and turn it into a product that is used by thousands now. So I'm going to share a little bit of my journey of my time at university and how I ended up to where we are today. So the beginning, the origin of my journey was really at Edinburgh University when I joined as a computer science and electronics student. During my first year, I had the chance, as many other students, to try a few sports, and before then, I'd never really done any sport in my life before. I was your typical geek, but I took a really keen liking to archery. The only trouble was that I was rubbish, and being a lack of funding and just sort of general help in archery, being a niche sport, I had only really myself to help myself improve in it. So I embarked on a journey whereby I took it upon myself to see if I could leverage my skill and my learnings in computer science and electronics to develop something that could help me improve my performance in my hobby. I started by placing sensors onto my body. These were EMG sensors and accelerometers, trying to measure my performance to build an algorithm that would take the data I collected, correlated to the arrow score, to see if I could spot any trends. And immediately there were a few startling tells that I started to use to refine my technique. I developed the way that this worked was that I would, wires and all, shoot a training session that consists of 60, 100 arrows, log every arrow, and corresponded to its associated data. And by building this database of what good, bad, and average look like, I would start to be able to inform myself of where I needed to focus my training. Doing this for about a year and a half, I was able to improve my performance significantly from a beginner to competing for the Scottish national team at the equivalent of the Commonwealth Games, and then I competed for my home country, Thailand, at the World Championships. I was actually on track to go to the 2016 Olympics in Rio, but an unfortunate car accident meant that I missed the opportunity to go. having tested this technology on myself, I had a bit more refined product to try and test it on another subject. So I ran an experiment where I took a beginner who'd never picked up a bow before, trained her, wired her up with my sensors, and trained her using the output of the algorithms I developed. And I managed to take her from a beginner to competing for Scotland in 6 months, breaking my own record. And it was really at that point that we realized that we had something that could be used. It had general applications, but there was no money in archery to try and commercialize it in. What we built, and these are images from way back in the day, was a way to solve quite a big problem that we saw in wearables at the time, was that most of the wearables only capture performance-related data, so your speed, your acceleration, your heart rate. Nothing actually captured the technique by which you applied to your sport. So we set out to build and embed sensors into clothing that allowed us to capture the 3D movements of the body, relay it to an external device, analyze it, and interpret it for the user to help them improve. We spent the last 3 years refining this technology and embedding it into lightweight clothing. So in the image on the right, you see a cyclist wearing a garment we designed alongside a very large cycling manufacturer with sensors embedded into it. So we managed to miniaturize our sensors and also develop manufacturing techniques that allow us to apply, to integrate our sensors into clothing and allow the clothing to be machine washed as would a normal user would, and allow users to use the clothes like they would normally would. On the left, this is an example of one of the applications that we're targeting. This will be one of the world's first sort of commercial products around measuring cyclists' aerodynamic efficiency while they're out in the field. The whole point of this product is that cyclists throughout what is known already is that cyclists throughout their run or their run, they will actually lose track of the most aerodynamic position over the course of run, and this leads to loss of up to minutes of potential time, especially in time trialing scenarios. So what we've done is that by being able to capture the body position and know what the optimal body position is, we're able to feed back through a display and haptic sensors to feedback when the cyclist is in correct body position. And this is one of the applications that we'll be launching towards the end of this year. An alternate use, which we're also exploring at the moment for our sensing technology, is in the use in back posture monitoring. We have found that we can embed our sensors into clothing, as you see on the left, such that it can be integrated to really lightweight undergarment fabric, and we can actually capture we can capture data on different points in the back to give a better to give a better look of how you're slouching rather than whether you're slouching or not, which is the current status quo in the market. And our focus in building these sensors into the clothing themselves instead of an external device you stick onto you has always been driven by what we expect, what we see as the optimal user experience. For an end user to be able to just take a shirt that they normally do, put it on, and that have all the integrated sensors, batteries, and modules ready to go is for us an optimal and the most user, the best user experience. We also, which is currently out in the market, we also work with team sports. So we developed a control module not particularly groundbreaking, that measures position on a pitch via GPS, accelerations via multiple axis IMUs, and feeds this back to a coach for them to be able to better plan training loads, help the athletes who are injured recover and train safely. And what is novel about our approach in this is that we have again focused on a good user experience. The status quo in the market of these is that you usually require a sports scientist to be there. These units will output, and they claim to output hundreds of metrics, which the poor sports scientist then has to make sense of and then translate to the coach. We worked out what were the key metrics, how we can combine these 100 raw metrics into 2 or 3 key metrics that are easily presentable to the coach directly, so that they can make the decision themselves of what action they could take. It's all about the user experience for us. We our products work across a variety of platforms, so we support iOS, Android, and the web. This is just a few screenshots of what's currently out there with us. We are also able on our team product to give insight to coaches in real time, which is starting to become the norm. But we're able to provide the key data that these coaches need at the sidelines during a match, during a match scenario, which gives them and what we've seen happen is gives them a big edge over the competitors who don't, because they can now see actionable data around the player's performance to make the right strategic decisions during a game. We launched the team product in January this year, and so far signed up, we're over 1,000 users now. But over the course of the last 7 months, we've seen teams that are working with us achieve real results. From a numbers perspective, we see double-digit increases in intensity versus first halves and second halves in games. We see an overall increase in intensity that the player is operating at. And what this actually translates into the real world is that these, and we've been struggling to find a way to try to quantify this more effectively, is that these clubs are winning more games and they're getting promoted. Where this technology is having a big effect on the teams that we're working with. A slight look into the future. I've talked a little bit about more of the wearables that we're working on. We're now starting to look at vision-based applications to go with our to accompany our technology. And this is a project that we're working on at the moment with a couple students from the University of Edinburgh in more for internal tooling. But what we're trying to do is to scrape the internet for football videos to be able to build up a database of what a goal looks like from a position perspective, what a corner looks like, what a free kick looks like, because we can then take those models and overlay it onto our GPS data, which gives a top-down perspective, and then present to the coaches, look, during this match session that you uploaded, we think that you scored 2 goals, you conceded 1 goal, there were 10 corners, and these were the corners and these were the times. Now, previously, you would have to have somebody re-watch that video, and there are paid services for this, where somebody will watch the whole match video and tag all the events in it. We're currently exploring this as an opportunity at the moment. The last 3 years has been very interesting and a bit of a roller coaster. We started with myself and Hayden, who were both on the same degree program, and we're now at a team of 14 across multiple disciplines. And if there's anybody who's interested in working with us from a collaboration perspective, I'll be more than, we do some work with the University of Edinburgh already, but I'm more than happy to pass my details so we can have a chat.
Okay, thanks, Roy. That was a really fantastic talk, and a great way to close off the session today. It was particularly interesting to see things from a slightly different perspective. That we've had the kind of academic input, and now we see the more commercial, industrial side of things. Although your journey, you did start here at Edinburgh University, and graduated with a Bachelor in Engineering honours in Computer Science and Electrical Engineering back in 2016, and it seems like you've been doing really well for yourself since then. If we have any questions, you can now raise your hand or type them in the chat. My first question, which I'm sure you probably get quite often, is just in general, do you have any advice for fledgling startup companies or those who want to push their career in this sort of direction?
See, general advice is I get this question a lot, and it's very hard to give specific advice. It really depends on what you're trying to do. But the most general piece of advice I can give is building a startup is very, very difficult if you're not passionate about what you're doing. So I get people to kind of just think about if they're trying to create something because they want to create it, or they're actually because they want to create a startup and go through that journey, or is because they have a really good idea, passionate about something, and want to see it through. It's very taxing. It's a lot of hours, but the best piece of advice, like I said, is you've got to have the passion and the drive. But if you have both, then you will succeed.
Okay, thanks. I have one more question, just on applying this sort of technology competitively, especially in something like the Olympics. There might be some athletes that can afford to access technology like this, and some that can't. And just from a standpoint of like fairness and equity in competitive sports, do you see this being an issue or something that has to be controlled? Or
one thing that I didn't actually mention in the talk, I probably should, is that the reason why I started Player Data was actually seeing that inequality from my own from my own experience. Was seeing that as you go up the chain, you get more and more tools and toys to play with, and there's more money thrown at you, and I saw that as very unfair. So what Player Data has set out to do is to make this technology as accessible as possible to anybody who really wants to use it. Most of the football clubs that we work with are at amateur level and semi-pro level. They're not your top flight Rangers or Celtics. But the funny thing is that we're running testing sessions with a couple of amateur sides at the moment, and at their matches they're now better kitted out than your Celtics and Rangers because of us, because we've been able to make it accessible. And that's something that is, you're right, is an absolute problem, but that's something that we're looking to change.
okay, yeah, that's really great to hear. So I don't think we have any more questions from the audience. So I hope you'll all join me in thanking all of our speakers today, Dr. Amjadi, Professor Rogers, Dr. Nazarpour, and the CEO of Player Data, Roy Hotravanon. Yeah, it was a really interesting event, some fascinating talks, and thank you all for coming. Thank you to the speakers for sharing some of your work with us. I will just quickly close out the session by talking about what SISMA has planned in the future. So if you just give me a moment to share my screen. So you can follow CISMA's activity at our Twitter handle, CISMA_colloquia. The next event that we'll be doing is on the 17th of September, which will be another webinar, this time on scientific ethics, and it's in collaboration with OSA student chapter at the Politecnico di Milano. The following month, on the 3rd of November, we're going to have the future of intelligent sensing and measurement, which will hopefully be an in-person seminar, and it'll be covering biosensors and artificial intelligence. There will also be a poster session at this event, so if anyone is interested in presenting their own work there, keep an eye out for emails from CISMA or follow us on Twitter, so you can keep up to date with everything. And we should be sending out a call for posters for that event quite soon. So that's everything from me. If there's any further questions, you can post them in the chat, and if the speakers are happy to stay around for a little bit longer and answer them. But aside from that, just please join me in the chat in thanking all of our speakers for taking time out of their busy schedules and coming to share their really exciting and groundbreaking work with us. So yeah, thank you from me on behalf of all of CISMA. Thank you.